This page describes energy efficiency in means of transportation. For the environmental impact assessment of a given product or service throughout its lifespan, see Life Cycle Assessment. The energy efficiency of different types of transportation ranges from some hundred kilojoules per kilometre for a bicycle to several megajoules for a helicopter. Units of measurement: efficiency can be expressed in terms of distance per vehicle per unit fuel volume, distance per vehicle per unit fuel mass, volume of fuel consumed per unit distance per vehicle, volume of fuel consumed per unit distance per passenger, volume of fuel consumed per unit distance per unit mass of cargo transported. Transportation types: for freight transport, rail and ship transport are generally much more efficient than trucking, and air freight is much less efficient. Walking a 68 kilograms person walking at 4 kilometers per hour requires approximately 210 kilocalories of food energy per hour, which is equivalent to 4.55 kilometers per megajoule. 1 US gallon of gasoline contains about 114,000 British thermal units of energy, so this is approximately equivalent to 360 miles per US gallon. Flammable. Flammables seem to have the highest energy efficiency in personal transportation. At a speed of 50 km per hour, the UAW manufacturer claims they need only 0.5 kWh of food energy per 100 km to transport the passenger, which is around 1/5 of a normal bicycle, and 1/50th of an average fossil fuel or electric car. This corresponds to 4,700 miles per US gallon. Other sources give a figure of 1/3.4 of the energy efficiency of a normal bicycle. Bicycling a relatively light and slow vehicle with low friction tires and an efficient chain-driven drivetrain. The bicycle is one of the most energy-efficient forms of transport. A 64 kg cyclist riding at 16 km per hour requires about half the energy per unit distance of walking, 43 kilocalories per mile, 27 kilocalories per kilometer, or 3.1 kWh per 100 kilometers. This converts to about 732 mpg US. This figure depends on the speed and mass of the rider. Greater speeds give higher air drag and heavier riders consume more energy per unit distance. A motorized bicycle such as the Velocilex allows human power and the assistance of a 49 cm 3 engine, giving a range of 160 to 200 mpg US. Electric pedal-assisted bikes run on as little as 1.0 kWh per 100 km, while maintaining speeds in excess of 30 km per hour. These best-case figures rely on a human doing 70% of the work, with around 3.6 megajoules per 100 km coming from the motor. Human power including the human energy dramatically changes the efficiency of cycles quoted above. As with walking, this would include the increase in food consumption due to caloric efficiency of human muscle and cardiovascular efficiency. However, only the rise in food consumption above the diet of a non-cyclist should be considered. To be thorough, a comparison must also consider the energy costs of producing, transporting and packaging of fuel, the energy incurred in disposing of exhaust waste, and the energy costs of manufacturing the vehicle. This last can be significant given that walking requires little or no special equipment, while automobiles, for example, require a great deal of energy to produce and have relatively short lifespans. In addition, any comparison of electric vehicles and liquid-fueled vehicles must include the fuel consumed in the power station to generate the electricity. In the UK, for instance, the efficiency of the electricity generation and distribution system is around 0.40. Automobiles. Automobile fuel efficiency is most commonly expressed in terms of the volume of fuel consumed per 100 kilometers, but in some countries it is more commonly expressed in terms of the distance per volume fuel consumed. This is complicated by the different energy content of fuels such as petrol and diesel. The Oak Ridge National Laboratory states that the energy content of unleaded gasoline is 115,000 British thermal units per US gallon compared to 130,500 British thermal units per US gallon for diesel. A second important consideration is the energy costs of producing energy. Biofuels, electricity and hydrogen, for instance, have significant energy inputs in their production. Because of this, the 50 to 70% efficiency of hydrogen production has to be combined with the vehicle efficiency to yield net efficiency. A third consideration to take into account is the occupancy rate of the vehicle. As the number of passengers per vehicle increases, the consumption per unit distance per vehicle increases. However, this increase is slight compared to the reduction in consumption per unit distance per passenger. We can compare, for instance, the estimated average occupancy rate of about 1.3 passengers per car in the San Francisco Bay Area to the 2006 UK estimated average of 1.58. Finally, vehicle energy efficiency calculations would be misleading without factoring the energy cost of producing the vehicle itself. This initial energy cost can of course be depreciated over the life of the vehicle to calculate an average energy efficiency over its effective lifespan. In other words, vehicles that take a lot of energy to produce and are used for relatively short periods will require a great deal more energy over their effective lifespan than those that do not, and are therefore much less energy efficient than they may otherwise seem. Compare, for example, walking, which requires no special equipment at all, and an automobile, produced and shipped from another country, and made from parts manufactured around the world from raw materials and minerals mined and processed elsewhere again, and used for a limited number of years. It has been researched that driving practices and vehicles can be modified to improve their energy efficiency by about 15%. Example consumption figures. Solar cars use no fuel, charging the batteries entirely from built-in solar panels, and typically use less than 3 kWh per 100 miles. The 4-passenger GM Enya uses 169 Wh per mile or 10.4 kWh/100 kilometers, which equates to 2.6 kWh/100 kilometers per person when fully occupied, albeit at only 24 miles per hour. The General Motors EV1 was rated in a test with a charging efficiency of 373 Wh/c mile or 23 kWh per 100 kilometers. Chevrolet Volt in full electric mode uses 36 kWh per 100 miles, meaning it may be more energy efficient than walking for 4 or more passengers. Note that the energy at the power station is more than this by approximately 2.5 times. The Daihatsu Charade 993cc's turbo diesel won the Most Fuel-Efficient Vehicle award for going round the United Kingdom consuming an average of 2.82 L/100 kilometers. It was surpassed only recently by the VW Loophole 3L, which consumes about 2.77 L/100 kilometers. Both cars are rare to find on the popular market. The Daihatsu had major problems with rust and structural safety, which contributes to its rarity and the quite short production run. The Volkswagen Polo 1.4 TDI Blue Emotion and the Seat Ibiza 1.4 TDI EcoMotion, both rated at 3.8 L/100 kilometers, were the most fuel-efficient cars on sale in the UK as of March 22, 2008. Honda Insight Euro achieves 48 mpg US under real-world conditions. Honda Civic Hybrid regularly averages around 45 mpg US. Toyota Prius Euro. According to the US EPA's revised estimates, the combined fuel consumption for the 2008 Prius is 46 mpg US, making it the most fuel-efficient United States car of 2008. In the UK, the official fuel consumption figure for the Prius is 4.3 L/100 kilometers. 2012 Cadillac CTS V-Wagon 6.2 L supercharged, 14 mpg US. 2012 Bugatti Veyron, 10 mpg US. Aircraft equals. A principal determinant of energy consumption in aircraft is drag, which must be opposed by thrust for the aircraft to progress. Drag is proportional to the lift required for flight, which is equal to the weight of the aircraft. As induced drag increases with weight, mass reduction, with improvements in engine efficiency and reductions in aerodynamic drag, has been a principal source of efficiency gains in aircraft, with a rule of thumb being that a 1% weight reduction corresponds to around a 0.75% reduction in fuel consumption. Flight altitude affects engine efficiency. Jet engine efficiency increases at altitude up to the tropopause, the temperature minimum of the atmosphere. At lower temperatures, the Carnot efficiency is higher. Jet engine efficiency is also increased at high speeds, but above about Mach 0.85 the airframe aerodynamic losses increase faster. Compressibility effects, beginning at transonic speeds of around Mach 0.85, shock waves form increasing drag. For supersonic flight, it is difficult to achieve a lift-to-drag ratio greater than 5, and fuel consumption is increased in proportion. Passenger airplanes averaged 4.8 L/100 km per passenger in 1998. Note that on average 20% of seats are left unoccupied. Jet aircraft efficiencies are improving. Between 1960 and 2000 there was a 55% overall fuel efficiency gain. Most of the improvements in efficiency were gained in the first decade when jet craft first came into widespread commercial use. Compared to advanced piston engine airliners of the 1950s, current jet airliners are only marginally more efficient per passenger mile. Between 1971 and 1998 the fleet average annual improvement per available seat kilometre was estimated at 2.4%. Concorde, the supersonic transport, managed about 17 passenger miles to the imperial gallon. Similar to a business jet, but much worse than a subsonic turbofan aircraft. Airbus states a fuel rate consumption of their A380 at less than 3 L/100 km per passenger. As over 80% of the fully laden takeoff weight of a modern aircraft such as the Airbus A380 is craft and fuel, there remains considerable room for future improvements in fuel efficiency. The mass of an aircraft can be reduced by using lightweight materials such as titanium, carbon fiber and other composite plastics. Expensive materials may be used, if the reduction of mass justifies the price of materials through improved fuel efficiency. The improvements achieved in fuel efficiency by mass reduction, reduces the amount of fuel that needs to be carried. This further reduces the mass of the aircraft and therefore enables further gains in fuel efficiency. For example, the Airbus A380 design includes multiple lightweight materials. Airbus has showcased wingtip devices that can achieve 3.5% reduction in fuel consumption. There are wingtip devices on the Airbus A380. Further developed Minix winglets have been said to offer 6% reduction in fuel consumption. Winglets at the tip of an aircraft wing can be retrofitted to any airplane, and smooths out the wingtip vortex, reducing the aircraft's wing drag. NASA and Boeing are conducting tests on a 500-pound blended wing aircraft. This design allows for greater fuel efficiency since the whole craft produces lift, not just the wings. The blended wing body concept offers advantages in structural, aerodynamic and operating efficiencies over today's more conventional fuselage and wing designs. These features translate into greater range, fuel economy, reliability and life cycle savings, as well as lower manufacturing costs. NASA has created a cruise-efficient STOL concept. Fraunhofer Institute for Manufacturing Engineering and Applied Materials Research have researched a shark skin imitating paint that would reduce drag through a riblet effect. Aircraft are a major potential application for new technologies such as aluminium metal foam and nanotechnology such as the shark skin imitating paint. Propfan propulsors are a more fuel-efficient technology than jets or turboprops, but turboprops have an optimum speed below about 450 miles per hour. This speed is less than used with jets by major airlines today. However, the decrease in speed reduces drag. With the current high price for jet fuel and the emphasis on engine airframe efficiency to reduce emissions, there is renewed interest in the Propfan concept for jetliners that might come into service beyond the Boeing 787 and Airbus A350XWB. For instance, Airbus has patented aircraft designs with twin rear-mounted counter-rotating propanes. NASA has conducted an advanced turboprop project, where they researched a variable-pitch propfan that produced less noise and achieved high speeds. Related to fuel efficiency is the impact of aviation emissions on climate. Small aircraft, motor gliders made of composite materials can reach an extremely low fuel consumption for cross-country flights, using thermal air currents and winds. At 160 km per hour, A diesel-powered two-seater diesel burns 6 liters of fuel per hour, 1.9 liters per 100 passenger km, at 220 kilometers per hour. A four-seater 100 horsepower MCR4S burns 20 liters of gas per hour, 2.2 liters per 100 passenger km. Under continuous motorized flight at 225 kilometers per hour, a pipistrel sinus burns 11 liters of fuel per flight hour. Carrying 2 people aboard, it operates at 2.4 liters per 100 passenger km. Ultralight aircraft Tecnam P-92 Eco Classic at cruise speed of 185 km per hour burns 17 liters of fuel per flight hour, 4.6 liters per 100 passenger km. Other modern ultralight aircraft have increased efficiency. Tecnam P-2002 Sierra RG at cruise speed of 237 km per hour burns 17 liters of fuel per flight hour, 3.6 liters per 100 passenger km. Two-seater and four-seater flying at 250 km per hour with old generation engines can burn 25 to 40 liters per flight hour, 3 to 5 liters per 100 passenger km. The Sikorsky S-76C++ twin-turbine helicopter gets about 1.65 mpg US at 140 knots and carries 12 for about 19.8 passenger miles per gallon. Ships equals. Queen Elizabeth. Cunard states that the RMS Queen Elizabeth II travels 49.5 feet per imperial gallon of diesel oil, and that it has a passenger capacity of 1777. Thus carrying 1777 passengers, we can calculate an efficiency of 16.7 passenger miles per imperial gallon. Maersk uses a WAC currency RTSILA currency Sulsara TA96E, which consumes 163 GKYH and 13,000 kg per hour. If it carries 13,000 containers, then 1 kilogram fuel transports 1 container for 1 hour over a distance of 45 kilometers. The ship takes 18 days from Tanjung to Rotterdam, 11 from Tanjung to Suez, and 7 from Suez to Rotterdam, which is roughly 430 hours, and has 80 MW, plus 30 MW. 18 days at a mean speed of 25 knots gives a total distance of 10,800 nautical miles. Sailboats. A sailboat, much like a solar car, can locomote without consuming any fuel. However, often energy will be needed for demands other than propulsion, such as cooking, heating or lighting. The fuel efficiency of a single-occupancy boat is highly dependent on the size of its engine, the speed at which it travels, and its displacement. Due to the high viscosity of water, with a single passenger, the equivalent energy efficiency will be lower than in a car, train, or plane. Trains can be an efficient means of transport for freight and passengers. Efficiency varies significantly with passenger loads, and losses incurred in electricity generation and supply, and, importantly, end-to-end delivery, where stations are not the originating final destinations of a journey. Actual consumption depends on gradients, maximum speeds, loading and stopping patterns. Data produced for the European Meat project illustrate the different consumption patterns over several track sections. The results show the consumption for a German ICE high-speed train varied from around 19 to 33 kWh per kilometre. The data also reflects the weight of the train per passenger. For example, TGV double-deck duplex trains use lightweight materials, which keep axle loads down and reduce damage to track and also save energy. Freight. Energy consumption estimates for rail freight vary widely, and many are provided by interested parties. Some are tabulated below. Passenger. Considering only the energy spent to move the train, and taking as example the urban area of Lisbon, train seems to be on average 20 times more efficient than automobile for transportation of passengers, if we consider energy spent per passenger km. Considering an automobile which has a consumptions of around 6L/100 km of gasoline, the fact that on average cars in Europe have an occupation ratio of around 1.2 passengers per automobile and that 1 litre of gasoline amounts for about 8826 Wh, one gets on average 441 Wh per passenger km. On the other hand, a modern urban train with an average occupation of 20% of total capacity, which has a consumption of about 8.5 kWh per kilometre, one gets 21.5 Wh per passenger km, 20 times less than the automobile. Braking losses. Stopping is a considerable source of inefficiency. Modern electric trains like the Shinkansen use regenerative braking to return current into the catenary while they brake. A Siemens study indicated that regenerative braking might recover 41.6% of the total energy consumed. The passenger rail and scheduled intercity and all charter bus industries' technological and operational improvements. A Eurofinal report states that commuter operations can dissipate more than half of their total traction energy in braking for stops, and that we estimate head-end power to be 35% of total energy consumed by commuter railways. Having to accelerate and decelerate a heavy train load of people at every stop is inefficient despite regenerative braking, which can recover typically around 20% of the energy wasted in braking. Weight is a determinant of braking losses. Other references: AEA study of road and rail for the United Kingdom Department for Transport, final report. Buses equals. In July 2005, the average occupancy for buses in the UK was stated to be 9. The fleet of 244 40-foot 1982 New Flyer trolley buses in local service with BC Transit in Vancouver, Canada, in 1994/95 used 35,454,170 kilowatt-hours for 12,966,285 vehicle km, or 9.84 megajoules vehicle km. Exact ridership on trolley buses is not known, but with all 34 seats filled this equates to 0.32 megajoules passenger km. It is quite common to see people standing on Vancouver trolley buses. This is a service with many stops per kilometre. Part of the reason for the efficiency is the use of regenerative braking. A commuter service in Santa Barbara, California, USA, found average diesel bus efficiency of 6.0 mpg US. With all 55 seats filled, this equates to 330 passenger mpg. With 70% filled, 231 passenger mpg. At an average load of 9 people, the efficiency would be 54 passenger mpg and could be half of this figure when many stops are made in urban routes. In 2011, the fleet of 752 buses in the city of Lisbon had an average speed of 14.4 km per hour and an average occupancy of 20.1 passengers per vehicle. Rockets equals. Unlike other forms of transportation, rockets are commonly designed for putting objects into orbit. Once in sufficiently high orbit, objects have almost negligible air drag, and the orbits decay so slowly that a satellite can be still orbiting decades after launch. For these reasons, rocket and space propulsion efficiency is rarely measured in terms of distance per unit of fuel, but in terms of specific impulse, which gives how much change in momentum can be obtained from a unit of propellant. NASA's Space Shuttle fires its engines for around 8.5 minutes, consuming 1,000 tons of solid propellant and an additional 2 million liters of liquid propellant to lift the 100,000 kilograms vehicle to an altitude of 111 kilometers and an orbital velocity of 30,000 kilometers per hour. With a specific energy of 31 megajoules per kilogram for aluminum and 143 megajoules per kilogram for liquid hydrogen, the vehicle consumes around 5 TJ of solid propellant and 15 TJ of hydrogen fuel. NASA's crawler transporter is used to move the shuttle from storage to the launch pad. It uses diesel and has one of the highest fuel consumption rates on record, 150 US gallons per mile. International transport comparisons. UK public transport rail and bus are generally required to serve off-peak and rural services, which by their nature have lower loads than city bus routes and intercity train lines. Moreover, due to their walk-on ticketing, it is much harder to match daily demand and passenger numbers. As a consequence, the overall load factor on UK railways is 35% or 90 people per train. Conversely, air services work on point-to-point networks between large population centres and are pre-book in nature. Using yield management, overall loads can be raised to around 70 to 90%. However, recently intercity train operators have been using similar techniques, with loads reaching typically 71% overall for TGV services in France and a similar figure for the UK's Virgin Trains services. For emissions, the electricity generating source needs to be taken into account. U.S. passenger transportation equals. The U.S. Transportation Energy Data Book states the following figures for passenger transportation in 2009. U.S. freight transportation equals. The U.S. Transportation Energy Book states the following figures for freight transportation in 2010. From 1960 to 2010 the efficiency of air freight has increased 75%, mostly due to more efficient jet engines. 1 U.S. gallon of fuel can move a ton of cargo 857 kilometers by barge, or 337 kilometers by rail, or 98 kilometers by truck. Compare, Space Shuttle used to transport freight to the other side of the Earth, 40 megajoules per ton-kilometer. Net energy for lifting, 10 megajoules per ton-kilometer. Canadian transportation equals. Natural Resources Canada's Office of Energy Efficiency publishes annual statistics regarding the efficiency of the entire Canadian fleet. For researchers, these fuel consumption estimates are more realistic than the fuel consumption ratings of new vehicles, as they represent the real-world driving conditions, including extreme weather and traffic. The annual report is called Energy Efficiency Trends Analysis. There are dozens of tables illustrating trends in energy consumption expressed in energy per passenger km or energy per ton km. Caveats: comparing fuel efficiency in transportation has several challenges. All transportation methods require a different infrastructure. The building, repairing and renovation of this must also be considered, and heavy usage of infrastructure will require earlier maintenance, which will also be energy-consuming. Road transport requires an extensive network of well-maintained paved roads, and trains require railroads and stations along the whole length of the track. Meanwhile, ships and aircraft only require a more limited amount of harbors or airports, without any en route infrastructure except for the occasional navigation beacon. Some types of transportation can take shorter routes, thereby offsetting an increase in energy consumption per unit of distance traveled. For example, a trip from the UK to Italy would take a boat an enormous detour via the Strait of Gibraltar, while cars need to travel much less distance. A train can cross through the Channel Tunnel, and aircraft can take by the shortest route or, in case of favourable winds, a more efficient route. There is a distinction between vehicle MPGE and passenger MPGE. Most of these entries cite passenger MPGE even if not explicitly stated. It is important not to compare energy figures that relate to dissimilar journeys. An airline jet cannot be used for an urban commute, so when comparing aircraft with cars the car figures must take this into account. There is currently no agreed method of comparing electric vehicle efficiency to heat engine vehicle efficiency, but typical emissions and thermal energy consumption can be compared. Vehicle speed is also an important parameter, and a peer-reviewed evaluation which involves these criteria may be found at http://bentham-org-2ev001/11toefjpdf. If the issue is rapid investment in new electric mass transit, it is important to use emissions associated with the most polluting fuel because increased demand for electricity increases the use of polluting fuel used in generation for the immediate future, as well as low emissions fuels in the case of some countries. Systems that reuse vehicles like trains and buses can't be directly compared to vehicles that get parked at their destination. They use energy to return for more passengers and must sometimes run on schedules and routes with little patronage. These factors greatly affect overall system efficiencies. The energy costs of accumulating load need to be included. In the case of most mass transit, distributing and accumulating load over many stops means that passenger kilometers are inherently a small proportion of vehicle kilometers. See Transport Energy Metrics, Lessons from the West Coast Main Line Modernisation and Figures for London Underground and Transport Statistics for Great Britain 2003. Lessons from the West Coast Main Line modernisation suggest that long passenger rail should operate at less than 40% capacity utilisation, and for London Underground the figure is probably less than 15%. Most cars run at less than full capacity, with the usual average load being between 1 and 2. Cars are also subject to inefficiencies because of congestion and the need to negotiate road junctions. The impact of transport road building to reduce congestion should always be considered, as should the improving efficiency of cars. See http www.hm-treasury.gov.uk9 PBS CSR07 King 840 PDF. Vehicles are not isolated systems. They usually form a part of larger systems whose design inherently determines energy consumption. Judging the value of transport systems by comparing the performance of their vehicles alone can be misleading. For instance, metro systems may have a poor energy efficiency per passenger kilometre, but their high throughput and low physical footprint makes the existence of high urban population densities viable. Total energy consumption per capita declines sharply as population density increases, since journeys become shorter. See also Logistics and Transport Focus Vol 9 No. 10 through Volume 10 No. 6 for a series of articles debating the general issues of fuel efficiency in transportation in the context of impact on climate change. Footnotes. See also, ACEA Agreement, Alternative Propulsion, Corporate Average Fuel Economy, Carbon Dioxide Equivalent and Emission Standard, Gasoline Gallon Equivalent, Gas Guzzler, Sustainable Transport Environmental Calculator of the French Environment and Energy Agency. External links, ECCM Study for Rail, Road and Air Journeys between main UK cities, 1, Flight Emission Calculator, Transport Energy Consumption Discussion Paper 2004 Euro Professor Roger Kemp Traction Summary Report 2007 Professor Roger Kemp Transportation Energy Data Book, Fuel Consumption Ratings, Energy Efficiency of Different Modes of Transportation by James Strickland, MSc. Stanford, 2009.